My name is Jason from ETH Zurich. So I'm glad to stand here to present our work on unified deep structure model for 2D pose estimation in videos. This work is in collaboration with Limin, Wang, Van, and Otmar Hilliges. So I just realized all the works here are most 3Ds. I don't know why I'm in this session actually. Recently, deep learning has drastically improved 2D human pose estimation. Fully convolutional architectures have been deployed to tackle this joint regression problem. To summarize, after getting the head map from convolutional layers, current deep architectures can be roughly grouped into two categories. The first one category stacks regress head maps and the original image as a new input for the next multiple stage convolution again. While the second category incorporates spatial relationship in order to explicitly refine the regressed head maps. So however, when we directly deploy these models, these networks on current video dataset, we still see several challenges. For example, most current video datasets have relatively low resolution. So when the faces are not so clear, there is still the problem of double counting symmetric body parts. So you can see the video, there are two clear modes in the heat map. Another main issue for many video sequences is motion blur. And you can see here, when the motion blur happens, the heat maps are not that tight. Although there are several changes in videos, we can exploit additional information, which is that human poses are temporally consistent in sequence. Prior work has tried to use chain models to capture long-range temporal dependencies, but this makes assumptions that our regular motion have patterns. Or directly propagate joint position estimate from previous frame to the current frame by optic flow. Others have used spatial-temporal models on top of the joint regressor for pose estimation in videos or pose tracking in videos. However, the optimization of the graphic model is independent of the feature learning process. Similar to previous work, we embed a spatial and the temporal model which exploit temporal consistency and try to optimize labeling frames jointly. But unlike prior work, we build an end-to-end trainable framework. This means we incorporate spatial-temporal constraint into the convolutional network training to jointly optimize the convolutional filters and also the spatial-temporal graph parameters together. In more detail, given a slice of video sequence, fully convolutional layers first regress joint confidence maps for each input frame. These heat maps are then sent into flow open layer. Our goal is to improve temporal stability of joint prediction. We do not incorporate an explicit motion pattern, but instead deploy dense optic flow to propagate information temporally. Specifically, this layer ops the body parts heat maps by pixel-wise dense optic flow so that they align with its labeling frame. In our current implementation, we compute optic flow offline. Finally, both the optic heat maps and the heat maps directly from convolutional layers pass through the inference layer. This layer conducts inference between body parts spatially and temporally, producing the final joint prediction. The core part is the spatial-temporal inference layer. In terms of modeling, each vertex corresponds to one of the body parts. Each blue edge represents a collection between two of these parts spatially. The single image pose estimation problem can then be formulated as maximizing the score S given image I. Phi is the unit term for the body part I, and psi is a prerequisite term modeling the spatial compatibility of two labeling parts I and J. Given a slice of video sequence, the temporal links are introduced among neighboring frames in order to impose temporal consistency. The object function is then the summation of the scores of single frames and the prerequisite term of the temporal link. The elements of the temporal link are the current prediction and the flow opt prediction from neighboring frame. We represent both spatial and temporal prerequisite terms by spring models, where the parameter omega encodes relative location and rigidity between pairs. Importantly, these parameters are optimized with the convolutional weights together in an end-to-end manner. In terms of inference, because for looping models, exact inference is in hard. So in order to maximize the overall score, looping belief propagation algorithms was applied. For each iteration, the score of part I is the summation of its unary and the message passed from its spatial and temporal neighbors. For example, the score of elbow is equal to the unary term plus the message passed from shoulder and also the previous frame's elbow. Generally, the message passed from part K to part I is based on the score of part K and the spring model between I and K. This maximization process can be efficiently solved by the generalized distance algorithm. As for the end-to-end training, because the resulting max location for message passing has been stored, similar to the max pooling operation, the backpropagation can be achieved through subgradient descent. The gradient for the parameter of spring models can also be calculated by the chain rule. So together with the weights inside the convolutional layers, all the parameters are optimized jointly. Here we show some quantitative result. This column is the ground truth. This column is just from convolutional layers. This is the result after just spatial inference. And the last one is our result when incorporating both spatial and temporal inference. You can see here heat maps are getting tighter and also more accurate when more evidence are introduced during training. This is the symmetry example we mentioned at the beginning. Compared to the baseline model, which is just from the fully convolutional layers, our model can make the heat map more accurate. And for the motion blur example, heat maps are getting tighter. And this is a video for comparison on all the joints. So generally, we can say that with spatial temporal information, the estimation are more stable. But still, there's failures when extreme motion blur happens or when the poles are very, very irregular. So here we demonstrate some quantitative result on Penn Action dataset. We can see that with spatial temporal information, the result outperform baseline model along the PCK threshold axis for flexible body parts like ankles and knees. Even in the strict region, the performance is improved by a relatively large margin. And this is the accuracy table for PCK threshold and 0.2. So if you are interested in the detailed accuracy for each joint, please refer to the paper. Here we mainly discuss the overall mean performance. So compared to the baseline model, the spatial information bring around 4% increase. Introducing temporal information, another 5% can be added. By freezing the convolutional layers, the accuracy is around 4% lower than the end-to-end optimization. And not surprisingly, after end-to-end training, the basic convolution layers can gain a 4% performance boost. This proves that joint optimization also helps the convolution layers to learn better feature representation. So in terms of limitations, the first thing is that right now, optic flow extraction is outside the network. So in the future work, state-of-the-art deep learning-based optic flow exchanger could be integrated into the framework to enable real-time inference. Sixth thing is that when long-range motion blur happens, the system still fails. And in general, current video-based pose datasets are still relatively small because we know the annotation is very, very difficult and expensive. And also they are in relatively low resolution. Okay, thank you. Any questions?
So we have time for questions.
Hi, I was wondering if you could comment on like the kinematics of the individual body parts, how they move through the video. Did you learn, for instance, that feet are moving more rapidly than hands, and maybe what that means in terms of predicting where those parts are when they're occluded or unseen in a particular frame?
Sorry, could you repeat again a little bit slower?
So the model is able to use adjacent frames to help the prediction. So how do you do when certain parts are occluded then in one frame, but they were seen in previous frames? Can it predict from those trajectories where they might be better than if you just did it from the structure of the body in that one frame itself?
Yes, actually it's from both. Yes, sometimes the temporal information can give you a direction, and also the body model can roughly give a lot of evidence to help you elevate this occlusion problem.
Okay, thanks. And then I was also trying to ask whether you think the model is learning that specifically, say, one model for feet versus a separate model for shoulders that don't move quite as much. Feet move more than shoulders. Is your model learning the ways that feet move that are different than shoulders, say?
Sorry, again, so maybe, can you explain again?
I'll try maybe in a different way. Like, do you think the model is learning that arms and legs move faster than the head moves?
Yeah, I think also, spatially, of course, we have some configuration with the body parts, yeah. And also a lot of things, like currently, the video-based data set, they're action-specific. So I guess maybe also the motions somehow also be learned a little bit in temporarily here. Yeah.
Okay, thank you.
Other questions? I'll ask a question. Since some of your examples were with sports like baseball pitchers and such, it's known that professional baseball pitchers can have very different joint action than people like me, for example. So are you training on professional athletes or training on?
Because I think right now, because to be fair to compare, so I think our model has to be trained on each data set, on that data set, and test on that data set. So as I said, right now, currently the video-based pose data set are mainly sports or action. So yeah.
Okay.
So it's mainly the professional. Yeah, that's what I mean. We need a bigger, more general video data set.
Okay, thank you. Anything else? Okay.